going to be one of the more critical lessons because we're really getting a firm introduction to logarithms. So let's think about how are exponential functions and logarithmic functions related? Hopefully, if you've been paying attention, you know they are inverses. Really, really important. So just like when we add, we subtract, because adding and subtracting are inverses. When we multiply, we divide to solve equations because multiply and divide are inverses. Add and subtract, inverses. Multiply, divide, inverses. Exponential logarithm functions, inverses. So think about back when we first started learning addition, way back in whatever grade you did that. We could write every addition statement as an equivalent subtraction statement. So 2 plus 3 equals 5 could also be written as 5 minus 3 equals 2. 7 plus 3 equals 10 can be written as 10 minus 7 equals 3. Just like addition and subtraction can be rewritten as equivalent statements, therefore, every exponential equation can be rewritten as a logarithm equation and vice versa. For example, log base 2 of 32 equals 5 could be rewritten as an exponential function. The one thing they will always have in common is the base. So remember, this is the base of the log, the only part that is subscripted. The base of the log always becomes the base exponentially. They always will match. The base of the log turns into the base exponentially. So it also should make sense for the logarithm, you're going to see the word log. For exponent, you're not going to see log, you're just going to see an exponent. So basically, just like we up here, we use the numbers 2, 3, and 5 in the addition. We also use 5, 3, and 2 in the subtraction. We didn't find any answers. We didn't simplify. We just rewrote. I'm going to use the numbers 2, 32, and 5, but write as an exponent. So what order should we put the 32 and the 5 in if 2 is the base? Well, if you look at your card, you know 2 to the 5th power equals 32. So this is the logarithm equation. This is the exponential. So you can use this statement for every single rewriting. If you start with the exponential, then use this for the logarithm. If you start with this with the logarithm, use this for the exponential. This is like the basic format for every single one. So for example, we identify the base of the log is 125. We start with the base exponentially, 125. And sometimes I even call it the circle. Start with the base, go around. Base 125 raised to the 2/3 equals 25. Don't solve anything, don't simplify, just rewrite using all the same numbers. Start at the base of the log, 8, move around to the 1/3 power equals 2. Then we just go backwards. Log base 4, so the base in the log is always subscripted. Make sure it's always smaller and lower than everything else, of 64 equals 3. Log base 3 of 1/27 equals -3. Now, I want you to ponder, why is it that log base 4 of 64 equals 3? Now, if you look at your card, what does 64 equal? 64 is 4 to the third. So does it make sense that this whole logarithm equals 3? We know log base 4 is the inverse of exponential base 4. Logs and exponential functions are inverses. So if the bases are the same, they cancel each other out, and the answer is the exponent every single time. So the big idea in evaluating logs is match the bases. All right, so that's all we're going to do on this entire page. If you have your card out, it's really handy because I'm going to be substituting using powers that match my bases. So I'm going to bring down log base 5. I need to replace 125 with 5 because that matches my base. 5 to what power is 125? 5 to the third is 125. So log base 5 cancels out the exponential base 5, and my answer is 3. Try letter B. We bring down log base 3. We need to replace 81 with 3 to a power. 3 to the fourth power is 81. I replaced 81 with 3 to the fourth. Log base 3 cancels out the base 3. 4 is my answer. Always, we're just going to bring down log base 2. 64 is 2 to the 6th. Match the bases. They cancel. The exponent 6 is the answer. All right, so those first 3 are pretty straightforward. The next 3 are just a little bit trickier. So if I bring down log base 7, I can replace 49 with a power of 7, but that is still in the denominator. 1 over 7 squared. I can't cancel until I move it to the top because it needs to be 7 to a power. Well, if the 7 squared's in the denominator, I can move it up and make it to the negative exponent. Now they're both bases, so the bases cancel, and my exponent is -2. E is one of the harder ones. So let's think about this. I can see that 25 can be replaced with a power of 5, but I can't make 5 a power of 25. So what I'm going to do is replace 25 with 5 squared in the base. It's really important. 5 squared is all lowercase down there. And I'm going to say 5 is just 5 to the first, because any number without an exponent is just to the first power. Then my log base 5s cancel, and watch this carefully. I'm now left with 1 over 2. 1/2 is my final answer. So I'm left with the 1 over 2 because it's just the 5s that cancel. Letter F is the same thing, but I have to change both bases. Both 64 and 16 can be rewritten using a base of 4. 64 is 4 to the third, all down in the base of the log. 16 is 4 to the second. So my base 4's cancel. I'm left with 2 over 3, 2/3. Now, okay, so letter A is the easiest problem I've given you all day if you've been paying attention. The bases match right away. It's just 8. What's important is it doesn't matter. Logs and exponents are inverses. It does not matter if the log comes first or if the exponent comes first. You might not be able to tell, but it's 3 raised to the log base 3 of 4x minus 1. So the base exponentially is 3. The base of the log is 3. So whatever is left when you cancel the bases is your final answer.